Hello and assalamu alaikum, everybody. This is a group assignment for EEE 3124 subject. The topic we selected to discuss for our assignment is Kelvin bridge. Before we start, let us introduce ourselves. My name is Mohammad Tanzim Rashid and my metric number is 204928.
My name is Zaki Muhammad Zaki Al Hashmi and my metric number is 205039.
My name is Hisham Abdul Samad Al Dahbali. My metric number is 204715.
My name is Anibasi Uchukube and my matric number is 199977.
Next slide, please. Okay, so today's group discussion will cover the contents shown on the screen. We will first go through the introduction of Kelvin bridge network design, then system design and operation. Following that will be the formula derivation and examples of its application. Advantages and disadvantages of the system will be elaborated before we finish our discussion with the conclusion. Okay, next slide. Okay, so first, what is a Kelvin bridge? It is a network design abbreviated from Wheatstone bridge. It is used to measure unknown resistors having low resistance, that is lower than 1 ohm. It eliminates or greatly reduces the effect of lead and contact resistance, allowing us to get a more accurate result. This network design was first invented by Sir William Thomson, who is also known as Lord Kelvin. In 1861, Lord Kelvin invented this design. In some countries, this network is also known as Thomson Bridge or Kelvin-Rubble Bridge. Okay, next slide, please. This certain network design has its own instrument, which can be used as a portable device and used in any sort of circuit to measure the resistance. The ports in the device are connected to the lead wires and then with the load wires. Below the P and C ports is the port for connecting sensitive galvanometer. The sensitive galvanometer is used for the detecting the balance condition. The lead wires are connected between the P and C port of the same charge, while the load resistors is connected to the C ports. To find the corresponding balance condition, the galvanometer should have no current flow through it while measuring. That's all from my part. Thank you.
All right, now I'll be taking over from Tanzim. Next slide, please. The Kelvin bridge, which is used to measure very low resistances and is a variant of the Wheatstone bridge, operating similarly to it, but using two additional resistors. The operation can be explained by starting with a standard Wheatstone bridge set to measuring low resistances, meaning that when the null detector indicates 0 voltage, we know that the bridge is balanced and the ratios Ra over Rx and Rm over Rn are mathematically equal to each other. The red E-wire symbols in the figure are substantial voltage drops caused by substantial stray resistances which are generated from the connections and wires between the low resistance resistors Ra and Rx. These substantial voltage drops will end up affecting the null detector's readings and thus the balance of the bridge. Next slide, please. To avoid measuring these substantial stray resistances and only measure Rx, the null detector and Rm over Rn ratio arms are directly connected across the ends of Ra and Rx, which will make the E-wire voltage drops nearest to the DC voltage source terminals relevant to the null detector's readings. Next slide, please. The remaining E-wire stray voltage drops can be managed by making the connection path between the lower end of Ra and the upper end of Rx substantially resistive by adding two resistors and sizing them so that their ratio from upper to lower is the same ratio as the two ratio arms on the other side of the null detector. Thus, the Kelvin bridge circuit is complete. That's all for my part. Thank you.
Okay, so now we'll go over the derivation of the to find the equation that we will be using to evaluate the value of Rx from our circuit. So looking at this circuit, this is looking at this circuit, which is an equivalent circuit of the Kelvin's bridge, showing all the connections, including the two additional arms resistors A and B. So we first have to evaluate and see the relationship between the arm uh, I IK and the arm IMC. The arm IK is parallel to the arm IMC, so the voltage drop will equal as shown in the equation number 1. After that, we can so now we can show the total voltage drop across the electrical potential across the whole of the circuit is equal to the total current I multiplied by the equivalent resistance of the circuit. Now, to find the electrical potential across R2, which is across the arm IK, it's equals to the ratio R2 over R1 plus R2 multiplied by the value of the total electrical potential that we found in the previous line. After that, to find the electrical potential across the arm IMS, which is parallel to IK, we just have to find the voltage drop across R3 and RP, which is shown here. By substituting equation number 2 and equation number 3 in our first equation, equation number 1, we will get this, and then by simplifying the line, deleting the equal terms of both sides, canceling equal terms of both sides, such as the current, and the resistance, we will simplify this equation to get this for our Rx value. So we'll be using this equation to evaluate the Rx value in Kelvin's bridge. Under two conditions, specific conditions, we can simplify these equations. So the two conditions is when R1 over R2 ratio is equals to A over B, and the null detector indicates balance, which is 0. The previous equation could be rewritten as Rx equals R1 over R3, R1 over R2 multiplied by R3, which is equation number 5. To show like how could we use how to use this equation, we will show an example. So there's an example given that the ratio RA over RB is equal to 0.01, and that the R3 over R3 equals 6. Find Rx. We know that from the circuit, RA over RB equals to the R1 over R2. So therefore, we can directly solve the equation Rx equals R1 over R2 multiplied by R3, which will give us a value of 0.0006 ohms. I will hand it to Basil.
Okay, now I'm going to talk on the advantage and disadvantage of this Kelvin bridge, which these are the advantage. We have about 4 advantages of it. One of it is that this Kelvin bridge can be used to measure a small amount of resistance between the range of 0.1 micro to 1 micro ohm to 1 ohm. And also the power consumption of this system is less, and it is simple in construction as well. And the sensitivity also is high. Next slide. And we have the 3 disadvantages of this system, which one of it is manual adjustments are to be made periodically when it is required. And in Kelvin bridge as well, sensitive galvanometer is used to balance, to detect the balance condition. And high measurement current is also required in obtaining a good sensitivity. Yeah, next slide. Next slide. So in conclusion, we've already defined, given a short introduction on what Kelvin bridge is, and also what is it? We've also heard about the description from the second speaker, and the derivative of the formulas from the third speaker. And lastly, we can conclude that Kelvin bridge is a modified form of a Wheatstone bridge, which is used to measure a small amount of resistance value range from 1 ohm to 0.1 micro ohm, which is 1.0 times 10 to the power minus 7 ohms. So thank you guys for listening, and this is all we have.